Amazing. All right. Welcome everyone in the room and everyone on Zoom to our seminar. So I'm delighted to introduce Amit Seta, who's coming from ANU to visit. Amit is a research fellow at ANU in the Research School of Astronomy and Astrophysics, and he's working a lot on cosmic rays and magnetic fields in galaxies and all this wonderful stuff. So we're going to learn a lot about cosmic rays and magnetic fields, I hope. So I'll take, Amit, why don't you take it away?
Thank you. So, hello everyone. First of all, I'd like to thank Salim for the invitation and for Kieran, Tarak, and all students for the organization and taking care of me. So, yeah, I'm Amit, and today I'm planning to talk about cosmic rays in spatially intermittent magnetic fields. As I go about, I'll explain part of this sentence. And I'll give a very brief introduction to start with, get some numbers through of what I'm assuming, and then I'll talk about my research. So this has some brief introduction to start. So let's start from the beginning. So cosmic rays are relativistically charged particles, but the story begins in 1912 when Victor Hess went in a balloon flight and realized that as you go, as the altitude increases, the radiation increases. Such a simple experiment made the fact clear that the radiation is not coming from the Earth, it's coming from outer space. And this radiation was termed by Millikan, this is Millikan of the famous Millikan oil drop experiment, as cosmic rays. So initially when cosmic rays, Victor Hess got a Nobel Prize in 1936 for the discovery of cosmic rays. And he was quite thorough. So he went in day, then he went in night, because people said, oh, maybe sun is doing something. And so he was quite thorough, and he went up to like roughly 5 kilometer height. So these were the first balloon experiments for cosmic rays. So the only conclusion then was that there is this radiation which is coming from outer space. It's not terrestrial. This confirms that.
The online audience is requesting that you stand there so
Sorry,
that they can see you.
Yeah, sure. So this was the, I would say, discovery of cosmic rays. Now we know a lot about cosmic rays. So cosmic rays are basically relativistically charged particles. What I'm showing here is like a number plot. So basically you can read y-axis as some normalized way of number of particles and x-axis as the energy of that particle. And you see it has a huge range. It goes from like 1 GeV to almost 10 to the power 11 to the power 12 GeV. So this is the, and there's the power law of some minus 2.7 or minus 3, whatever. But the basic idea is that there is you get particles in a huge range of energies. Of course, the number of particles goes down. An interesting thing to also observe expense which helped to build this plot. And if you look at energies, you have also energies much higher than you get in LHC. The x-axis has some typical numbers. So basically, you get these particles from outer space. They are relativistically charged. They come in a range of energies with varying number densities, because the number changes with energy. And generally, they are divided into 3 categories. One is very low energy particles, less than 1 GeV. Then the GeV energies, which are a lot. There are also various types. So it's proton, electrons, also some heavier charged particles. And then there is ultra-high-energy cosmic rays, which has energies greater than 10 to 9 GeV. So this is what we roughly know now in a very simplistic term. So the first question is, where does this energy come from? Like, how are they so energy? How are they gaining so much energy? And the GeV cosmic rays, the middle bit and the lower bit, are accelerated in supernova shock by Fermi acceleration. So it's also again a very textbook case. Basically, what happens? You have a shock front moving, and then the thermal particle, not the relativistically charged energetic particle, normal thermal gas particles bounce back and forth as the shock is moving this way, and with each bouncing they get energy from the shock. So that's how the way and if this happens a lot of time with each going back and forth, they collect some energy and they eventually become quite energetic. In ISM, this happens in like supernova shocks. So this is one of a toy example I'm showing. So supernova is basically stars at the end of their life explode as supernova explosions. These explosions, the shell moves at a very high speed, and particles traverse back and forth on this shell, which is moving. They're bouncing off magnetic mirrors and they get their energy from that. So this is how they gain so much energy. It's mostly from supernova explosions. This is GeV case. For the ultra-energy cosmic rays, the source is not yet known. It's a matter of debate. So we are still trying to understand what could give rise to such a high energy in particles. Where does this? There is no free lunch in physics, right? If this energy is coming, it's coming from somewhere. So what is giving rise to this very high energy cosmic rays is not known yet. And that's one of the interests which I'll talk about at the end of my talk. Going ahead, so how much time do they spend in galaxies? Since stars are formed in galaxies, stars at the end of their life explode as supernova explosions. This supernova explosion accelerates cosmic ray particles, so the cosmic ray particles becomes energetic within a galaxy, not just ours, maybe various galaxies. So how much time do they spend in these galaxies before they leave and come to us if they are accelerating in other galaxies? So if you think of a simple case where you have a spiral Milky Way type these galaxies and a halo around it and a supernova explosion going off here, this is just my toy picture. They are at relativistic speed, so they just shoot out, right? You would naturally think so. And if you calculate the time scale, you will take a typical size of galaxy by a speed which is comparable to speed of light. So this is, if I put 10 kPa almost c, you get 10 to the power 4 here. So typical cosmic ray particle, if they are shooting as soon as their acceleration is done, they will stay for 10 to the power 4 years, leave the galaxy and come to us or go to other galaxies. But if you look at observations, they suggest something else. So what I'm showing is very old observations, but they're very intuitive. So what these guys have done is they have plotted on the top the isotopes of beryllium. So this is 7, 9, 8, 9, 10 in cosmic rays and in solar neighborhood. Now what happens is beryllium 9 and 10 are radioactive. So they are decaying with time. But beryllium 7 is not. So in galactic cosmic ray, we realize that the beryllium 9 and 10 are much lower than that of beryllium 7. But in solar neighborhood, all these components have roughly same has roughly the same number density. So if you do basic kinetics, that the number of beryllium 10, which is radioactive, divided by number of beryllium 7, which is not. And if you assume that beryllium 7 and 10 were produced in similar quantities, then you can do n by n naught, the beryllium 10 at start and beryllium 10 now, what you see in cosmic rays. And if you do this very simple calculation, this is like 50, the beryllium 10 is like 5. If you do very simple calculation, you get 10 to the power 7 years. So they're not shooting out. They're confined within the galaxy for a longer time than you would expect if they were just shooting. So the next natural question is to ask what's trapping these particles? Like if they are so energetically charged, why are they not just shooting out of galaxy? Why is it taking so long? What is keeping them so long? And so the propagation and the answer turns out to be that the propagation is not shooting out, it is like a random walk for GeV cosmic rays. So they are not just shooting out, they're going back and forth. They're doing this random walk business throughout the galaxy before they eventually leave the galaxy at a much longer time scale. And this random walk is introduced by magnetic fields. So that's why magnetic fields come into picture. So this idea dates back way longer in 1967 and in 70s. So the idea is basically, imagine if you have a uniform magnetic field. This is again a textbook problem. And if you have a charged particle, it just gyrates around. So this is gyrating. Suppose if the red line is uniform field. Now, if the magnetic field has a very small perturbation, it's not perfectly uniform, but a small perturbation, then the gyrating particle scatters. This idea was put forward then. So this is again a random process. So as soon as it encounters a fluctuation, it doesn't scatter. It scatters randomly. It's a random process. So some of the particles will be confined for a longer time than others, but eventually they are scattering. So one of the particles is going this way, another particle is going that way. So there are a lot of scattering events. This scattering leads to a random walk for an ensemble of particles, which leads to diffusion. So this idea is put forward. The diffusion is the main propagation mechanism of these particles, even though they are relativistically charged. They move at relativistic speeds, but they do that in a random walkway. So they never go out very quickly. It takes time. This is the first point. And of course, if you have something moving like this, then you would expect the distribution. If I look at one side and I look at the other side, the number of cosmic rays should be roughly equal, coming from all possible sides, right? And this has indeed been observed by these two setups. Because of their location, they probe different regions. And a very high degree of, so this is TeV, not even GeV, much higher energy, very high degree of isotope observed in the cosmic ray sky. So if I look at one direction, I measure number of particles, then I look at other direction, measure number of particles, the amount of isotropy is very high. And this isotropy further confirms, so with beryllium observations, this isotropy further confirms that the cosmic rays, the GeV cosmic rays, are confined, they're diffusing. And one could convert the level of asymmetry to a diffusion coefficient. It's just a pen paper calculation. Now, this is for low energy or GeV cosmic rays. What if I look for such a sky for an ultra energy cosmic rays? Then you see something like this. This is from Auger telescopes. So this is a very similar plot. This is some normalized particle count. This is a very similar plot as before, but now for ultra energy cosmic rays. You clearly see a dipole. I'll come to it in a second. But before that, they are not even accelerated in the galaxy, right? I was saying you, for GeV cosmic rays, the idea is settled that it's the supernova explosion accelerating them. But the question is, what about ultra energy cosmic rays? The source of acceleration is extragalactic. How do I know that? Again, if one does a simple calculation, so if I put cosmic ray energies at 10 to the power 9 GeV, ultra energy cosmic rays, the magnetic field has 5 microgauss. One can calculate Larmor radius is around 100 kiloparsecs. So Larmor radius, if you have a uniform field, the gyration radius is called Larmor radius. So this high energy particles has a Larmor radius which is 100 kiloparsec. It skips all of the galaxy in one go. So if it is not even trapped, it is not even confined by the galaxy, how can it accelerate? So this is certainly the source is extragalactic. It can't be accelerated within the galaxy. And this is the first point. The second point is that you see a dipole. And again, the why should one see a dipole is not clear yet. And if you do the CMB way of doing it, that it is basically the motion, then the amplitude of dipole doesn't agree. And I was discussing this with Oliver and Gerard about their work on is there some connection between CMB type dipole, and can we calculate things from this data? So this is another direction. So roughly the field is divided into two. One is the low energy GeV particles, which are accelerated in supernova shocks. They are the energy carrying component because the number density is quite high. And another is extragalactic ultra energy cosmic rays. And here the main question is, what accelerates the particles? Like how are this accelerated to this velocities? And they are connected to magnetic fields I was talking. So this is Planck polarization data. So it's again our Milky Way magnetic field map, you could say. And the first thing you look at this map, the first thing which comes to mind is this is probably created by artists. It's not scientists anymore. Like such a beautiful map. But then the second thing is that it's very rich in structure. There is the magnetic field is stronger in the disk. It has all kinds of these loops. the northern hemisphere is not really symmetric with the southern hemisphere. So it's a very complex and rich in its structure. And the most of the talk from here is how this structure of field connects with the cosmic rays propagation. Like how are these relativistically charged particles talking to such complex structure of field? So I was showing some toy cartoons till now. I'll put numbers to things. So the interstellar medium of galaxies, which is basically, as the name translates, stuff between stars, is a very rich medium, and I think sometimes the word doesn't justify the amount of richness it has. So it has gas, metals, dust, turbulence, magnetic field, and cosmic rays. Supernova explosion accelerate particles, which are called cosmic ray particles of GeV energy. Supernova explosion also drives turbulence. It's like stirring coffee. The natural stirrers in this medium. And the typical size of this turbulence is around 100 parsecs. So if you're stirring coffee, you will see fluctuations, but those fluctuations can't have a size greater than the size of the cup, right? Because that's the maximum. So in that sense, you have to think, though the medium is very large, this pockets where supernova explodes drives turbulence, which is around 100 parsecs. And this also amplifies magnetic field, which is around 5 microvolts. Now, what it turns out, if you put these numbers, the energy density of cosmic rays is comparable to other energy densities in the interstellar medium. So from a galaxy's point of view, this is a really important component. So the cosmic rays the 5G cosmic rays has to be considered if you are discussing the galaxy dynamics of galaxies. And for this talk, there are these two questions which I'll try to answer. So one, we were talking about Larmor radius of ultra-high-energy cosmic rays. But if you compute the Larmor radius of GeV cosmic rays, it turns out to be 10⁻⁶ parsecs, which is negligible compared to if the stirrer. So whatever magnetic field structure you put is very important because they are very attached to field lines. The Larmor radius is very small. The galactic magnetic fields, of course, doesn't help and add more complications that it's usually divided into two types. One is the large-scale ordered field and another small-scale turbulent field. When I say large-scale, I mean one magnetic field which has length scales much greater than the driving scale of turbulence. And when I say small-scale, the length scale much less than the driving scale of turbulence. So basically, the question is how are this small scale, and the small scale field is intermittent, I'll explain this term soon, but how does the structure of small scale field affects GeV particles and the ultra-energy cosmic rays? And one question is very important, like why should we care about cosmic rays, right? I usually think this way, that the first is because we are interested in physics of cosmic rays. We are interested in cosmic ray itself. But beyond that also, it's important to study cosmic rays because there is a variety of mechanisms in galaxies which are affected by cosmic rays, like synchrotron radiation, gas dynamics. It can heat up the ISM. It can be an additional source of heating. Then galactic winds. It can aid galactic winds, so that changes the evolution of galaxies. So the whole picture is that how does this complicated small-scale structure of magnetic field affect the propagation of low and high energy cosmic rays? Before going ahead, I would like to point out that magnetic fields are usually considered as nuisance also by people who work on magnetic fields, because it's usually very complicated and always not thought as the first thing that affects. But the picture is changing now globally. People are able to appreciate. In past decade, there has been a lot of studies where people appreciate the importance of magnetic field and cosmic rays. So yeah, so now pictorially, magnetic fields in galaxies. So large scale. So this is a nearby galaxy called M51. The background image is HST. The drapery pattern you see on top is a proxy for magnetic field. So this is very ordered magnetic field which goes with spiral pattern of the galaxy. This is the large scale field. And the small scale field is this jumbled up mess. It has all kinds of filaments. It has all kinds of structure. It's not very structured. So as you change the scale, you change the structure of the field. And most of this talk is about the small scale mess, tangled mess. To simplify this, one could just look at this picture. So the large scale fields behave something like this, that it is not turning. If you think of a 1 kiloparsec scale, it's not turning at all. But the small scale field is all tangled up mess. Now, if you imagine a cosmic ray particle attached to one of these lines, because its Larmor radius is very small, it just goes around this randomly. That gives rise to diffusion. So what structure you put in to find out how cosmic rays are propagating is important, because the field is that mess. Now I'll explain this term a bit called intermittency. So imagine a Gaussian distribution, a typical Gaussian distribution with mean 0 and standard deviation 1. And if I pick up random numbers, it will be something series like this. So this is called Gaussian distribution. The non-Gaussian distribution is something like this. So this is the term for intermittency or filaments or volume, not volume filling. The basic idea is you have very similar numbers as the Gaussian series, but once in a while you hit a very high peak. So it's mostly Gaussianized, you hit a high peak, it's again mostly Gaussian, you hit a high peak. So the magnetic field, the small scale magnetic field in galaxies is something like the second case. It's easier to see it in 3D where you have this filamentary structures. The field is not weak, the field is weak between the two, it's not non-zero, but you have this weak field, a filament, then a weak field and a filament. So observers usually call it filament, but for a theoretician, it's usually more like non-Gaussianity or spatially intermittent. One could look at it in a bit more detail from the PDF. So this is probably distribution function of a component of field from a simulation. If you had a Gaussian field, it will look like something like the red line. But a non-Gaussian field will look something like a blue line. So you have this high values of your random number, but they occur not as commonly. So the probability is low, but they are non-zero. They do exist. And the question is, how does this kind of field affect the propagation of particles if you give this structured field? And to do this, we first look at simulations. So basically, I pick up like a few kiloparsec, a maximum a kiloparsec size of box within galaxy, and just simulate what happens to magnetic field in there. And basically, you generate a magnetic field which is on the left-hand side. So this has this filamentary structure. You have a very strong filament. I'll come to what is in the right-hand side. And then you have a weak field in between. Then you have again strong filament. But it's still random. There is no coherence or order to it. Now to compare it, you take this field from a MHD simulation, take a Fourier transform of this, randomize all its phases, and take an inverse Fourier transform. Then you land up something which is on the right-hand side. So this two field has exactly same power spectrum by construction, but the structurally it's so much different. Here you don't have weak field. You don't have very strong or very weak field. Everything is like a Gaussian noise. So we'll look how particles propagate here and here. Then we know how does the structures is making difference. So this is I'm showing the power spectrum of both the Gaussian and non-Gaussian field, exactly same, which is by construction. But the PDF is different, as I was explaining. The non-Gaussian field has higher peaks. So it has same power spectra, structure function, correlation function, or any 2-point statistics. And a term which is usually used is the correlation length of field, which is like if I go from here to the cafe to have a coffee, I'm pretty sure I'll meet a UCED student. If I go to CBD, I'll probably meet a UCED student, but the probability has gone down. The probability of meeting a student is quite, especially in teaching. But if I go to Canberra, the probability is negligible. So this is basically a length scale up to which things are correlated with your starting point. And this can be computed from the power spectra, and it's exactly same for both the fields, but the structure is very different. So this is a very good control numerical experiment where we can find out how structure makes a difference. And to do this, now we have magnetic field, we have to put particles, right? To do this, we solve the Lorentz force equation, which is QV cross B. This is just some normalized, written in a normalized fashion. So basically, you put in magnetic field, which is structured and not structured, having same power spectra, and you put in a bunch of particles and see how they propagate. Now, when I was in my undergraduate and I read the first astrophysics paper, it was clear that with astronomy, there is some astrology going on. Because there are a range of numbers one has to decide even before one starts a simulation. And I used to always feel that there is some astrology, numerology going on in this. But with some experience, I can tell you they are very well, they're decided for a reason. And for this numerical setup, I'm saying you what are those reasons. So the first question is, like, how many number of particles should you choose? Is 100 particles sufficient, or do I need 10 to the power 6? So we, based on some numerical things, we decided 10 to the power 4. Like, what should be the time step? So if you find the fastest particle in your box, then if you are resolving the fastest particle, you are resolving all particles. Then how should we check? Questions like this, like maybe the computer is doing its own thing. You see, since we don't have electric field, the energy should be conserved. So what energy I have put in, the energy of those particles should be conserved. So we do all of these checks, and for the low energy particles, we find out what is the diffusion coefficient, basically from these particle positions, which is basically how much particles have traveled in some sense, like what's the length scale on which they're diffusing, the mean free path. And for ultra energy cosmic rays, we calculate the deflection angle. So this is a low energy particle from the simulation. This is a high energy particle in a spatially structured field. You see, and the curve is the strength of the field. So when the field is very strong, the particles is very faithful to the field line. It's just doing gyration. It's like a slave to the magnetic field. But when in the weaker field case, it does this random walk. It goes around randomly. For a low energy particle. For a very high energy particle, it just doesn't care. It deflects once in a while, because of course it's affected by magnetic fields, it's a charged particle. But doesn't do this random walk business. It just deflects once in a while. So the parameter is the ratio of this scale, where the Larmor radius comes from the whatever you assume about cosmic rays, and this correlation length comes from whatever you assume about the magnetic field. So a scale comes from magnetic field, a scale comes from cosmic rays, since we are trying to marry the both. The ratio of the scale is this parameter. Now this is the same trajectory shown for a bunch of particles. On the left-hand side, you see they become the spaghetti noodles I was talking about. Basically, they're diffusing, but the right-hand one just shifts a bit from their initial direction. So this is the diffusive propagation, and this is the non-diffusive propagation. So first, what we show here is the ratio of the diffusion coefficient in the spatially structured field divided by the randomized field. So at very low energies, at high energies, they both are same. So at high energies, it doesn't matter. But at low energies, the diffusion coefficient goes up for the structured field. Because in structured field, you have such big jumps. So it's like where the field is strong, it is trapped, but where field is weak, it is just jumping. So the mean free path goes up, and that increases the diffusion coefficient. And yeah, so this is just for a numerical interest. We can't, because to draw a circle, to numerically draw a circle, you at least need 8 to 10 points. So you have to resolve your Larmor radius with at least 8 to 10 points. So the minimum energy we go is 10 to the power 5 GeV. So if you extrapolate it more, the difference might be more. It's just numerically, it's not possible.
Could you just clarify what the different curves are there?
Yeah, okay. So yes, so this difference curves is basically looking at different kinds of intermittency, like different in structuredness also is varied a bit. But basically the dashed lines are the model, which I'll explain in the next slide, and the solid lines is from simulations. So simulation kind of agrees with model in terms of trend. And to explain this, we put forward a model. So if you think of a normal random walk, the drunk yard guy going to his home, there is no preferred angle. All possible angles, it can random walk. But for these cosmic ray particles, they have a preferred angle where the diffusion coefficient changes. So usually it is L square by T, the diffusion coefficient, but for a correlated random walk, it depends on the angle. So we had this idea of preferred angle connected to the size of the structures when you have structures. And this is, so now everything is computed numerically. This is the diffusion coefficient, and this is the preferred angle. And these are the randomized version are again dashes, and the solid versions are for the structured field. And we find out that both for the structured field and non-structured field, it's always a correlated random walk. There's a preferred angle. The preferred angle varies on a much larger scale for the structured field because the structures are not separated. So it's a correlated random walk and not a usual Brownian motion. This is a very theoretical idea, but we found this from our simulation. So the cosmic rays are doing a random walk, but it's a very non-trivial kind of random. They're diffusing, but because how they talk to structures and magnetic fields, it's a very non-linear, non-trivial kind of random walk. Going ahead, what I'm showing now is the PDF of deflection angle. Now we are talking about ultra-energy cosmic ray, which didn't do the jumble up, we just changed angle. And the different lines, the solid lines are for the structured field, intermittent field, and the dashes are for randomized field. And this is just different distances. It's a proxy for distance. We see overall they deflect less for intermittent field because they feel these gaps. So again, all possible angles are possible, but statistically they deflect less. So to see it in such a field, you have more deflection, but that happens once in a while only because they have this region where the field is very weak, they can just fly. But in a random Gaussian random field, the deflection is less, but it happens more frequently. So you're deflecting less, but you're deflecting throughout. So you ended up with a very different final location compared to where you start. Now, this was the particle sides of the whole thing. I'll take just a few minutes to discuss what I'm doing now. So it has been recently been appreciated that cosmic rays are also the GeV energy cosmic rays are very good feedback agents. They're very good in driving winds. And there are various kinds of fluid simulation, like on cosmological scales, on galaxy scales, on zoom in into galaxy, few kiloparsec scales. These are like simulations with JOS and TOR are also doing very similar kind of fluid simulations. Now we are taking gas as a fluid, cosmic ray as a fluid, magnetic field as an additional component. And the exact role in the evolution of galaxies or star formation is not really known. And we are trying to now include this in the next decadal plan for Australian astronomy, because the role of CR is being recently appreciated. And I'm also working a bit towards along that line. So I'll just explain it in 2 slides. So these are just first steps towards this. So this is having multi-phase magnetic field. So what I'm showing in a simulation, like exactly I was discussing before, this is density, temperature, velocity, and magnetic field. No cosmic rays yet. That is the ongoing work. It should have another panel with cosmic rays. And this is interesting for a plethora of reasons. But the main interesting bit is the structure of magnetic field changes with the phase. So if you are looking at the warmer ISM, where supernova explosion has just happened, it's a very different field compared to colder ISM where stars are forming. So the magnetic field now depends on the phase of the medium. So cosmic ray propagation will depend on the phase of the medium. It comes with this additional complication. And that's what my recent plan is. So what I'm showing here is from one of these simulations. Again, this is PDF of magnetic field. These are different curves for different phases of the medium now. The magnetic field is always non-Gaussian, so it's this complicated. It's not the Gaussian. And the magnetic field is statistically stronger in colder regions. It's not just, so it's the strength. Structurally, we also computed this called magnetic curvature, but it's basically trying to characterize numerically how much is the field curved. And we found that magnetic field is statistically more curved in the colder regions. So imagine like a particle on top of it, it will do a more efficient random walk if the field scales are smaller. So it will do a more efficient random walk in colder medium. Then hotter medium, it will do less efficient, more efficient. And how this comes up on galaxy properties is an open question, which I'm interested to follow. And we are now trying to join this idea with observations. So the first check is like, these ideas are not just in my head and in my computer simulation, but has to be confirmed with observations. So for that, we are using ASCAP data. And I'm just showing one slide here of a very recent work I'm working on. So basically the background color. So this is our neighbor, SMC, Small Magellanic Cloud. The background is neutral hydrogen column density. So these are neutral hydrogen observations. The white dots you see are neutral hydrogen absorptions. So these are colder regions. So the color in the background probes both warm and cold regions. The white dots probes colder regions. And the circles you see, blue and red, are magnetic field observations. This is rotation measure, just a detail. So basically we are trying, and all of this using the same telescope. So all telescope kinds of biases and all telescope kinds of things are same for all three observations. So the neutral hydrogen emission will tell us about warm medium, the neutral hydrogen absorption will tell us about cold medium, and this rotation measure observations will tell us about magnetic field. So we are now first trying to establish whatever simulation shows that the magnetic field is stronger and more curved in colder phases is also has signatures in observations now. That's an ongoing work. I'll quickly sum up now. So magnetic field structure is important for cosmic ray propagation. It's not captured by power spectrum alone. Then I showed low energy diffusion, cosmic ray diffusion is higher with intermittent structure, and this could be explained by a correlated random walk. And the amount of deflection for ultra-energy cosmic ray is less with intermittent structure because you have these gaps where these particles can fly. In ongoing work, I'm looking at how to characterize magnetic field structure using ASCAP observation and how to connect it with CR of the cosmic ray observation. And one big picture overall point is that this study of GeV cosmic rays is really multi-scale and multi-phase problem. Multi-phase, as I was explaining, because the magnetic field properties differs with the phase, but multi-phase, multi-scale because the physics, the pen paper physics is best known at Larmor scale. The simulations are at few parsec scales, and the observations are at hundreds of parsec scale. But there's a huge range of scales. It's 8 orders of magnitude going from very concrete theory to observations, which requires joining efforts and probes from various directions, not just simulations or observations, or one kinds of simulation or one kinds of observation. And I'll conclude this as just some of the references. Happy to answer any questions. Thank you.
Questions?
Yes.
So in terms of magnetic fields, we've had this solar astronomers doing this stuff for forever. And if Don Burrows was here now, we'd be reminded of all the things going on with the sun. Some people do local things, some people do the global thing, and eventually you want to connect. I've always had the worry that in the galaxy, we try to model the low order field, you mentioned rotation measures and scattering measures, of course. The low order field, the micro complex field. But what worries me is the low order field is not being modeled in terms of the dynamo, the galactic dynamo, because ultimately there is going to be a galactic dynamo. I know that Gensler's rotation measures and the other, or Sun and others, I can't remember all the teams, they do see it. They see like an octopolar structure. You see plus minus across the sky in both quadrants. So there really is a global field. And it seems to me that all this localized model, I know Christoph's and your work, I mean, Christoph has been doing stuff for ages. It's phenomenal, 12,000 cube simulations of turbulence. I mean, it's off the scale. But at the same time, we do want to connect all this micro localized weather stuff to a global setting if we can. Do you know what I'm saying? So have you seen any real attempts to model the dynamo, global dynamo?
Yeah, so
things that convince you at least that they know what they're doing.
Yeah, so I think this is a very interesting question. Basically, the way it happens is that these are two sides of the same coin.
Yeah.
In simulations, first let me talk about simulations. If you're not resolving small scale turbulence properly, you will not capture the large scale structures. It depends on what's happening at smaller scales. So it's important to resolve this, guys. And it's again, you know this with your work also, it's always a challenge, right? You want to resolve things on kiloparsec scale and less than tens of parsec scales. So this has always been a challenge. There has been some recent simulations, galaxy scale simulations, but none of them have seen a dynamo growth of large scale. I think that is yet to be seen.
Because like cosmology, where they simulate the universe and they zoom into what they really want to compare with.
Exactly.
But you could do that kind of thing with MHD for the galaxy. You could model it globally and then zoom in somewhere within the context of a global. I haven't seen anyone try that.
Yeah, I think this is not done. True, I agree. Yeah.
And I'd be more convinced if I saw it in a sort of an ecosystem setting.
Yeah, so all of this, like when you cut out this, to be fair, when you cut out this box, I'm just assuming, right, that the outflow and inflow are negligible, because in principle, everything is flowing in and out of this.
But you don't have any boundary condition there about the galaxy. It's
Exactly.
symmetric.
True, exactly. So I think this is not being addressed yet at the level, at least you are saying. There has been few attempts, but I think those were not with magnetic field. It was just hydro zoom in.
Okay.
But this is a difficult problem.
Oh, sure
right?
is.
I mean,
Yeah.
We've known in principle that the terrestrial magnetic field is of dynamo origin for 70 years.
Yeah.
No single person has produced a physically realistic,
It's a good point.
convincing real-world dynamo model that gives you, here's something that really looks like the core and really looks like the Earth, and here's something that comes out of it that really looks like the magnetic field.
It's a good analogy.
No, I mean, the scale is completely different, and the causality structure is completely different, right? I mean, it takes you a long time to get from one side.
But my analogy is with CDM. CDM, we model the whole universe, and then we go in and grab what we think of the Milky Way.
No, I understand.
Zoom into that.
Sure,
I'd
but
like to see us try that at least.
that there is a dynamo, I tend to believe, because of the correlation between the large scale structure and spiral arms, but to reproduce it, extremely demanding.
Yeah, but I meant just to go get the global thing happening, then go in and grab that, and then try and do a high res. In other words, your 12,000 cube simulations, to have a boundary condition that looks like it was in a dynamo, just in isolation in the middle of nowhere.
You need to find a Milky Way in the simulation. It doesn't necessarily have the internal structure.
No.
Yeah, the cosmological simulation suffers from the point that there is not. You have to do first zoom in to get a galaxy proper, then you have to do another zoom in to go even smaller scale. If you do it from cosmological simulation, it becomes a 2 zoom in question.
And my comment is really about the boundary condition of yours is a kiloparsec cube.
Yeah, it's like periodic.
Yeah, but that's purely symmetric, isn't it, on the boundary?
Yes. Yeah.
Oh, okay.
You don't impose any large scale shear or anything.
No. So I can tell you. So the way I think of this is these are like numerical experiments.
Yeah.
Not supposed to reproduce reality, or it's not even mimicking reality, I would say. It's just trying to find a structure. Like this is just establishing that structure matters. Yeah. But at what level and what exactly structure is a different question.
No, I mean, and it's very convincing at doing that.
Yeah.
But then you can compare to the map. I mean, to some extent, with going in the direction that just I think wants to go. I mean, you can compare with the map of a magnetic field that you have from.
Yeah, definitely.
Yeah. So like what we are trying to do is mostly to compare with observations. Like, because now the observation in rotation measures, since the observations are getting better and better.
Yeah.
I don't think people have, I mean, there have been work with like this illustrious TNG group has done some work in this direction. But I don't think none of them has seen a large scale dynamo in a simulation, because it needs all processes.
But I think Christoph is actually in a position to be the one of his German colleagues is in the position to do just that, to bring in global vorticity and global shear. Yeah, I know it's complicated.
Yeah.
But just you can forget the galaxy once you put in a realistic global vorticity.
Sure. Yeah.
But Christoph says, look, they've got so much to explore anyway. So he feels he's got a big agenda ahead of him anyway. But I mean, I'm hoping somebody somewhere.
Sure. Yeah, it's an interesting point. Yeah.
Because I think it does change things a lot.
Yeah. So you are saying, if I understand you correctly, you are saying not to model the whole disk, but to include large scale shear in the box.
Yeah, to include a realistic global, because we know it's very dominant and very important.
Sure.
Global shear, global vorticity.
Yeah.
Bring that in on some large scale.
Yeah.
I know people have tried cheating with
shear boundary.
shear boundaries, but anyway.
Okay. Yeah, I agree.
I have a related question for Joss, and it's just for clarification. So you mentioned this very striking thing that the energy density in the different components is of the same order of magnitude.
Yeah.
So your point from saying that is that until the cosmic rays go into the simulation, then you don't actually have a self-consistent treatment of the interstellar medium structure. That's the point.
Yeah, sure. I think it's an important, especially the GeV cosmic rays, and if you're interested, in like winds, then if you don't have in your simulations, if you're thinking from simulation point of view, if you don't have cosmic rays, then your wind characteristic might be different from when if you have cosmic rays. Because cosmic rays, so if you have a normal thermal wind, it cools down as it goes up. But the cosmic rays are relativistically charged particles. They have a much smaller cooling time, so they can pick it up the material for much longer heights. And this is intricately connected to evolution of like amount of gas in the disk and evolution of galaxies. So in that sense, I think it's an important component which must be at least considered. Even if not in a perfect form, but at least in terms of, if you're thinking of global simulation, at least in terms of cosmic ray pressure, like what pressure it affects where.
Can I ask,
Yes.
do you include any particle collisions when you do these diffusion of particles? I mean, is that negligible in comparison to the gyration around the magnetic field lines?
Yeah, so there is no collisions introduced. That really each particle doesn't talk to other particle, and that is true because all of these are going at relativistic speeds, and their primary way of communication is via magnetic fields. So if you think of a magnetic bottle, again a very textbook case, then if a particle is trapped, if another particle is trapped, they might interact, but that is via magnetic field. Particle-particle interactions are not included.
Well, what if I have like just some gas in the box? Will that be affected by the magnetic fields as well? And will if they're in one of these filaments, are they going to encounter a higher density of gas?
Yeah, so usually when you have, if you have this filamentary structure is connected to density, but they are not really same. Just a second, I think I have. Yeah, so if you think this is the density of the gas and this is the magnetic field, you have such small blobs here, it's a much longer. So how B depends on rho could be explored with these simulations, but it's again a very non-trivial dependence, not necessarily that where rho is high, B is high. So the magnetic field talks to density, and it at very small scale it might be strong to make some effect on the density, but generally it's subdominant.
Just a question right there. You did mention that there is some sort of correlation with temperature.
Yeah.
Where the gas is colder, the magnetic field is more intense, right?
Yeah.
That's interesting.
Yes.
Yeah.
So the strength is higher, like it's locally stronger because of density compression. But this density compression are not just changing the strength; they are also changing the structure. So it has smaller length scale. It's more tangled in the colder phase compared to the hotter phase.
What direction does the causation go there? Because when you were talking about your simulations, I had the impression that these filaments were sort of they were rising purely statistically. They were just sort of chance alignments in the field that comes from this non-Gaussianity, but it seems they're actually related to the gas. So
so it's the physics which affects it, because when you drive you drive a turbulence in a box, the magnetic field is determined by the induction equation, which introduces the filamentary structure. So it's the turbulence, which is, to be more specific, via the dynamo action introduces this filamentary structure. So it's the gas and the turbulence creating such filamentary structures.
So I had a related question about terminology.
Yes.
So you've called it both intermittent and turbulent, and you've also called it non-Gaussian. And unless I'm misunderstanding something, the non-Gaussian or non-Gaussian is not especially helpful as terminology because, right, I'm a particle physicist, not an astronomer, but non-Gaussian, I deal with lots of non-Gaussian things, right? They've got extra power in the tails.
Yeah.
You can put as much power in the tails as you like without necessarily making something filamentary.
Yeah, true.
And so why do you persist with the Gaussian terminology? Because other people use it and it's historical, or am I missing some detail?
Yeah, so I think I totally agree with you. Non-Gaussianity need not imply filamentary. But the point is in this, the filamentary terms basically comes from more of an observations, because in observations they see, oh, there is the rotation measure is higher here, or the magnetic field observable is higher here. So the magnetic field is filamentary. It's like what is visually seen. Like even simulation people, when they see this, it's filamentary. But one did not imply other. I totally agree. But in this community, all of these terms are used interchangeably, so I put all of them together. But I totally agree with you, like to be completely precise, the non-Gaussian, it is high power in tail, and filamentary is like shape, right?
But I mean, your high-powered toy simulation with the filamentary structure and then with the randomized phases was very convincing in this regard. That it really is it's the filamentary structure that's making the difference here.
Yeah, I'm not changing the scale at all. The scale is the same for both, right?
That if you're not capturing that structure, then you're missing out something essential, and no amount of adding an extra term or doing any other thing on the other side is going to help you. You've got to get this.
Sure. Yeah, that was the point. Yes. Yes.
This is a very naive question, but so you want to know the magnetic field to understand how cosmic rays move. Can you use cosmic rays to reconstruct the magnetic field, and how important would that be? Could you precisely reconstruct the magnetic field from the cosmic rays?
This is a very interesting question. It's very difficult because of this small scale mass. So the problem is like if I know the properties of this mass, then it's easy. Suppose if I don't know the properties of this mass, you can create degenerate scenarios in which you'll get this mass given the distribution of cosmic rays. So it becomes more degenerate if you go the other way. This way is a bit easier because once you decide magnetic field structure, it's easier to find out cosmic ray propagation.
I've seen claims that cosmic ray pressure change in radius, don't they? I've seen a FIT claiming it drops towards from MIT, it drops towards the galactic center because of a vast explosion of Fermi bubble.
Yeah.
That kind of thing. In terms of global.
In terms of global properties, you could say if you are seeing like lot of cosmic rays from a system, then probably it has weaker fields, like elliptical galaxies. You don't see synchrotron. So you can reverse engineer on a global scale. It's
get constraints.
What do you mean by C? I mean, you're not talking about actually detecting the cosmic rays. You're talking about detecting like synchrotron.
Yeah. So if you in elliptical galaxies, you have not in radio wavelengths. There is not convincing. Like from quiescent elliptical, of course, there is an AGN. So if you don't observe a synchrotron emission, then you can reverse engineering back that, since there is no synchrotron emission, so probably all cosmic ray electrons are flying out very quickly because probably the magnetic field is not strong enough to keep it in. But I usually find...
I think pressure is very interesting. If you model in terms of magnetic pressure, cosmic ray pressure and thermal pressure, and you forget the other ones now, radiative, there's a few more besides, but people have talked about the different variations in those pressures, the contributions on scale, radial, radius, vertical.
Height, yeah.
In terms of the actual cosmic rays, like the ones at the beginning, like the ones we physically detect, is there no useful information in that because of the sun? Or
so if you go to low energy ones, the sun is a problem. Sun is like below GeV. Sun is a big problem. I mean, that's why in this spectra also, I think they didn't put low energy ones because the solar modulation, even the Earth's magnetic field is scattering a lot. But here also, the GeV particles also is like the galactic magnetic field jumbles up everything. The problem is that if you just think in a very theoretical way, you can create degenerate scenarios like particles coming from this direction. And if you put a galactic magnetic field model, so this has to be solved in parallel, I think. And it is a bit of a point that though our magnetic field models and magnetic field data has gone much better, this has not really translated to cosmic ray propagation or cosmic ray physics in the same scale as the magnetic field.
But isn't there an energy window where it is informative?
Very high.
But but what about the top end of the energy range that is galactic? The radii are larger and the particles are stiffer, they retain more memory of their origin, and we know roughly what the density of supernovae explosions over the last 10 million years must have been.
Yeah.
Because they trace all the star formation.
There's an argument like that in Geis's book.
If you look at the ones that are low enough to be galactic, but high enough that they're relatively stiff, that must contain information.
But again, I think I agree with you, but I think to map it to field strength and structure is a different question, right? Like it does contain information.
But you could falsify certain scenarios, surely.
You need to know where they come from in the first place.
Yeah.
So you don't know where they come from.
But on the average, we do. They come from where the supernovae were, and the supernovae come from where the star formation is.
So they come from AGNs. They come
AGNs as well.
Everything.
I'm not sure about neutron stars and other things.
They could even come from dark matter.
Sure. No.
Microquasars.
But isn't
Your point's well taken, and also in terms of cosmic rays, in terms of the elements as well, elemental abundances.
Yeah.
Yeah, there's a whole. I think all atomic masses have.
Yeah, nitrogen, everything is there. Yeah.
And there's different characteristics for the different populations.
So I think picture like is quite complicated in that sense of going against going from cosmic ray distribution to magnetic field distribution.
Yeah, I always remember what Bruce was saying. I've seen in books, like Geisa has a book, the books, introductory books on cosmic rays.
Okay.
They go through simplistic models, and they end up concluding it's all a bit tangled.
Yeah.
You have these ways of thinking, but then
Yeah.
more and more information we have, it just seems that no one model fits anything.
Yeah.
Can I ask about
Yes,
this? The very beginning, you showed the sky map. You showed the two sky maps, one from, I guess, Auger, and then one previous to that, and you claimed it was isotropic, but then doesn't look. Yeah, so what the image you showed doesn't.
Sorry. Okay. Yeah, I don't think it's significant. I mean, if you look at, these are huge number counts, I should say, this are like 10 to the power 10. So it's statistical significance is there, to be fair. But I don't think the level of anisotropy is that high. And the way it is done is like you look at sources in that region and try to correlate with sources. This doesn't really correlate with any known sources. Because if the anisotropy correlates with some source, then you say, oh, it's coming from here, it's connected. But there is no real correlation. And here, we are not sure, because this is the ultra-high-energy, so they're not from galaxies. So here the problem is we are not sure where they are coming from. So this also can't be traced back. So the tracing back is usually an issue to its source. Because for low energy one, it is all jumbled up because of this interaction with magnetic field. And for very ultra-high-energy one, we don't know what the source is. Like
At the level of just the flux, ignoring anything about directionality, like are ultra-high energy cosmic rays expected to be dominated by a few nearby sources or dominated by a cosmological emission?
I think it's not known. So in this work, they have correlated it with like known galaxy distribution, and stuff like that. Like this is one of the known surveys, but there is no correlation with
What's the energy whereby the scattering of the CMB means they don't go more than a few hundred megaparsecs? There's some critical energy, isn't there?
Yeah, G is the cutoff. I think
Compared to
it's 10 to the power 10, 20 to the 20.
I might remember that number.
Yeah.
Get that plot, yeah.
Yeah, it's here. It's
Oh, it is that.
yeah, it is at very highs.
But we have seen
A bit there, yeah.
beyond that, haven't we?
But it's like 10 to the power 20 GeV. So it's almost. But by here, the number counts are so low that it's very difficult to take this forward.
But just to be clear, the CMB, scattering off the CMB means you don't go far between galaxies at 10 to the what? 10 to the 12? Is it the cutoff?
It should
That's
be
the
10 to
cutoff.
the
10 to the-
11 here because this is GeV.
All right. Oh, sorry, I've got the wrong unit.
Sorry, yeah.
GeV, there you are. 10 to the 20 EV, that's right. 10 to the 20 EV.
Does anyone on Zoom have a question? Now's your chance. Zoom no. Anyone else in the room? All right, well, let's close the session there. Thank you again.
Thank you.